Hello and welcome. In today's video, we're going to be going over topic 2.7, derivatives and rates of change. So, I want to start out by reviewing one of the most important things that we've learned so far, which is the difference quotient. So I have two difference quotient problems here. I'll give you a moment if you want to try them yourself, but I'm going to get started. So, for the first one, we want to start out by taking h plus 4 minus the square root of 4 all over h and multiplying that by the conjugate, which is h plus 4 still, but plus the square root of 4. And we can't really get this out of nowhere, so we're also going to divide it by h plus the square root of h plus 4 plus the square root of 4. Then we are going to see that this h, so this radical is going to cancel this radical, and this square root of 4 is going to cancel that square root of 4. And because it's the conjugate, we don't have to worry about the product or anything like that. So we are just going to get plus 4 minus 4. All right. Well, and then in the denominator, we're going to get h square root of h plus 4 and put that in plus the square root of 4. Well, we are going to then be able to cancel these 4's, as 4 minus 4 is just 0, and cancel these h's. So we are really just left with 1 over the square root of h plus 4 plus the square root of 4. All right, so that's going to be our first answer. Let's erase some stuff. Make some room. This is going to delete a bit more than what I wanted it to, but it's fine. Derivative, there we go. And then now I can select this and just drag it over. All right, let's work on the next problem real quickly. So this problem is going to be one where we need to cross multiply. So we're going to get 1 over h times by 1 over h plus 3 minus 1 over 3. We're going to cross multiply that. So we are going to get 1 over h times by 3 minus h minus 3 all over h plus 3 times by 3. Well, this 3 and this 3 are going to cancel. This negative is still there. And I want to change the size of that eraser. Alright. So we have a negative 3 and then a positive 3. Those cancel. We have this h, which cancels with that h. So you're really just left with negative 1 over h plus 3 times by 3. All right, let's clear off the board. And we're going to move this over here. So this last problem that I have for practice is just making sure you know the point slope form of a line. So we just need to know the slope, which we have here, and a point. So it goes as such: y minus y1 is equal to m times by x minus x1. So if we were to plug in all of the values that we know, we have y minus y1, which is 1, is equal to 4x minus 2. And that's going to be point slope form. So the next question that I want to, the first question I want to propose is, what is a derivative? Well, you may recall from unit 2.1, I believe it was, we introduced the tangent problem and the velocity problem. And this derivative solves both, actually. So what is a derivative? Well, I think the best way to show you is using this graph metric down here. So you may recall that we have a secant line between 2 points. Well, we can have a method for finding the slope. In fact, that method is like such. It's going to be f of x2 minus f of x1 all over x minus, x2 minus x1. Well, what if we want to get a better approximation for a tangent line, let's say? Well, we can get even closer. So let's say our new x is here. And this x is actually going to give us a bit better of an approximation. Alright, well, what if we now define another new x? What if x is now like this close to a? Well, we're going to get an even better approximation. So what I'm really supposing here is, what if we take the limit as x approaches a, and I want to delete this, but you're going to... Actually, you know what? I don't want to delete that. I want you to see the similarity. And we're going to have a point a, but we're going to say that we want f of x, which is, as we see over here, our right value, or our higher value, minus our f of a, all over x minus a. You can see the parallels between these two. And, in fact, all you have to do is slap a limit out front, and a secant line can become a tangent line. So what does a derivative actually do? Let's go over that now. Let's clear out this stuff. I want to move this definition of a limit over here somewhere. That works. Well, the first thing the derivative does, alright, is it is the slope of the tangent line. So, slope of tangent line. Slope of the tangent line. Alright, what else does it do? Well, it also represents rates of change. Well, what is a secant line? It's really just asking what is the average rate of change. So, a tangent line also represents a rate of change, but it's instantaneous. It's happening at a point. Alright. I forgot to write down the instantaneous part. Alright. Instantaneous rate of change. What is the another thing that it represents? Well, if it represents an instantaneous rate of change, you might recall that we also have a velocity problem. So it can also represent instantaneous velocity. Alright. Well, let's look at another definition of derivative. Well, or the alternate definition. And this is actually one I believe you're going to be more familiar with. So, we have this definition of the derivative, but we also have f prime of a. So f prime is really just saying the derivative at a point, evaluated here. It's another function, but we're going to get into that in more detail at the next video, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. That's the derivative. That's f prime of a. And more specifically, I need to say that this is at a and not x. It's just I'm used to writing x. So, looking at our graph, what this is really saying is, well, we have this h value here, and we're adding it onto our x. But as this h value gets smaller and smaller, we are going to take our approximations. Well, let's draw our first approximation line between these 2 points. There we go. Well, now let's say that we define this new x plus h. Well, if we define that tangent line, we're going to notice it's in a bit better of an approximation. And then we can also define one that's even better of an approximation. If my little wand here is going to let me. And as we take the limit as h approaches 0, we're going to find the tangent line. What happens, the instantaneous change at a point. Now you might ask, why can't we just say like f of a minus f of a and try and find the secant line or the tangent line that way? Well, this is going to always just evaluate to 0 over h. And that's not going to give us a slope. That's just always 0. And that doesn't help us at all. So we take a limit so we get infinitesimally close to our value a. Continuing on, I now have 2 practice problems I'd like us to work out together. So take a moment. If you want to try it, it's just a difference quotient with the limit. I think we all have the tools for that. Okay, so we're going to start out, multiply it by the conjugate. So we get square root of h plus 9 plus the square root of 9 all over the square root of h plus 9 plus the square root of 9. Well, this leaves us with the limit as h approaches 0 of h plus 9 minus 9 over h times by the square root of h plus 9 plus the square root of 9. Alright. Well, we can cancel these 9s up top. These h's are going to cancel. So, in the end, we are just left with this 1 over the square root of h plus 9 plus the square root of 9. Well, we're taking the limit as h approaches 0, so this is going to go to 0. So we get 1 over 6. Or our slope in this case, f prime of 9, is equal to 1/6. Or our slope of the secant line is 1/6. 2 ways to write it down. Okay, next problem, we're using the other definition of a derivative. And we are going to start out by bringing this x minus 2 out front. So we're going to take the limit as x approaches 2 of 1 over x minus 2 times by 1 over x minus 1/2. Well, how do we solve this? Well, we can cross multiply. So we're going to get the limit as x approaches 2 of 1 over x over 1 over x minus 2. And we're going to get 2, minus x all over 2x. Well, what are we going to do with that? Well, we can pull out a negative 1 from this, and we're going to get x minus 2, and we're just going to call that a negative 1. This x minus 2 and this x minus 2 will cancel, so we really get the limit as x approaches 2 of negative 1 over 2x. We can direct substitute this, so we get negative 1/4, or f prime of 2 is equal to negative 1/4. Our slope of our secant or tangent line is negative 1/4. Or this is another notation that you're going to get very familiar with once I start talking about rates of change. dy dx is equal to 1/4, or negative 1/4. All of these are equivalent. But you probably won't want to use this as function notation. I would like to specify that. So rates of change. So rates of change are, give me one moment. So recall that a rate of change, or average rate of change, so like average, or ROC can be abbreviated as, is change in y over change in x. Now, this is often like, if you're ever trying to find like a slope of a normal line, we will often call this like f of x2 minus f of x1 all over x2 minus x1. Well, suppose we take the limit. So we're going to just take the limit as the change in x approaches 0 of change in y over change in x. Well, once again, all of these values, and I'm still just going to call them x2, well, this is going to become closer and closer to a derivative, or the slope of the tangent line at x2. So, why do I want you to, know this? Well, I want you to just take a moment and think, what can this tell us? When might this be useful? Well, I want us to primarily take a look at this notation. Because this notation is really the basis of the dy dx. And what does this really mean? These d's really represent a very, very small very small increment. Small increment. So, but it still has the original variables in it. So, let's say I have a function that's giving me cost. So c, which is c is in cost. And we want to know how long is it going to cost. Let's say this cost is in time. And cost is just going up with time. Well, a thing that calculus is going to give us the tools for is if I take the derivative of this, so it's going to be dc dt, this tells us that this is really going to be cost per time. And you'll do this very often. You're going to be tracking units. This is a very applicable thing for science. But I really just want to highlight here that this derivative is the instantaneous rate of change of a function. So application to velocity, well, we know that velocity is given by the function like s of t, the displacement of t, or of an object. So, if I wanted to, say, find the velocity at a given point, well, velocity is distance divided by time. Well, if we have a function that gives us distance, like s of t, because s of t is displacement, if I take its derivative with respect to time, so we have ds dt, that is really just equal to our velocity. So, really, this derivative gives us a way to find the velocity of a function at any point. It gives us a way to find the slope of a tangent line at any point. It gives us the power of approximation. The derivative is such a powerful tool, especially if you're like an engineer or a physicist, chemist. So many useful fields. But I want to just give you like a really good example of what instantaneous velocity looks like. So we know how to find a derivative. So let's define velocity. Velocity of t is a limit as t approaches a of, let's say, s of t minus s of a all over t minus a. Well, what this is really saying is, as this t is going to approach a, we're going to get a better approximation for a, the tangent line at a. In fact, we're going to find the velocity at a. This derivative, as you're going to find, is very useful for finding rates of change. So I actually have an example here. So we want to find s of t is equal to 4.9 t squared and find its instantaneous velocity at 3 seconds. So we are going to take so we want to take our velocity. So we have v of 3 is equal to the limit as x approaches 3 of s of 3 minus s of t. I got that backwards, I apologize. So it's really s of t minus s of a all over t minus a. Okay. So we really can find this value out really easily. Okay. So we know that so we want to start out by saying that this is going to be 4.9. Let's see. 4.9 t squared minus 4.9 times by 3 squared all over t minus 3. Well, how do we want to solve this? Well, what can we do? Let's see. Or rather, it might be a bit easier to solve if we look at it from a different perspective. Let's try and using the other definition of a derivative. So we're actually going to say v of 3 is equal to the limit as h approaches 0 of s of 3 plus h minus s of 3 all over h. So what we're going to say instead is we're going to have 4.9 times by a t value. Oh, that's where my brain was. Okay, there we go. So 4.9, and we have this 3 plus h value squared. And then we have minus 4.9 t squared. Or, sorry, 3 squared. All over h. Well, I want to start out by factoring out this 4.9 to make my arithmetic easier later. And we're also going to, in the same step, just square this out. So we get 9 plus 6h plus h squared minus 9. Well, these two 9s are going to cancel, and this is still over h. And because we have this 9 factored out, we don't care about it, but we can also factor out an h. So I want to say that instead of calling this, we're going to call this 4.9h, we're going to then cancel the h's, So we get 4.9 times by 6, and then plus h. Well, we want to take the limit as h approaches 0. So this h is going to go to 0. And then we can quite literally just multiply it out. So we have 4.9 times by 6. Let's see, 6 times by 9, 54, I believe. And then 6 times by 4 is 24. So we get 29.4 as our answer. So our velocity at time is equal to 3 is really just 29.4 seconds, or meters per second, because it's displacement over time. It could also be feet per second, theoretically. So I'm going to give us an opportunity for plenty of practice. If you think you've gotten from the video, just feel free to leave, but I'm going to continue going. So, write an expression for a secant line of f of x at x is equal to 3. Okay, so we can do f of x plus, f of 3 plus h minus f of x is equal to, all over h is our secant line. So that's our answer for A. And let's use the other definition, or actually, let's use the same definition here. So we're going to then just take the limit as h approaches 0. And what you'll see is that these are similar. In fact, they are, just needs a difference of a limit. So, next thing, I have a very challenging problem. No, I'm kidding. It's not very challenging. So, I want us to really use all of the different forms of a limit. So, we're going to start out with this I to evaluate the tangent line. So, we know that we want to take the limit as x approaches a of f of x minus f of a all over x minus a. So this is like our background, but that's not what we're actually doing. But we want 0.1. So we're going to take the limit as x approaches 1 of f of 1 minus, f of x minus f of 1 all over x minus 1. Well, let's plug in some values here. We know that this is really just the limit as x approaches 1. F of x is x squared plus 3 minus f of 1, which is 4, all over x minus 1. Well, we will get the limit as x approaches a of x squared minus 1 all over x minus 1. X approaches 1. The limit as x approaches 1 then is just going to be, because this is the same thing as x minus 1, x plus 1, because it's a difference of squares, we can cancel. So we get just x plus 1. So we get 2. So I now have to, delete half of this. Alright. And our answer is 2. Make sure we don't confuse that. Okay. Let's go to II now. We want to use the other definition of a limit. So, we are going to do x squared. So we want x plus h, which is really going to be, so we want the limit as h approaches 0 of x squared, of x plus h squared plus 3 minus x squared minus 3 all over h. Well, this is just the limit as h approaches 0, and actually I want to just make sure I plug in a point here. 1, 1, alright. So we are going to then square this out, so we get 1 plus 2h plus h squared plus 3 minus 3 minus 1. Well, these 3's are going to cancel. That minus 1 and that are going to cancel, and all of this is over h. So we're just going to take the limit as h approaches 0 of 2h plus h squared all over h. This h is going to cancel all the h's up top. So we're just left with the limit as h approaches 0 of 2 plus h, which is quite literally just 2. So as we've shown here, these two expressions for the tangent line are equivalent. Alright, move that up there. And we're going to say that's our answer for II. Next one is find an equation. Well, we have a very easy method for finding equations. It's going to be just the slope of the secant line. Or sorry, not the slope of the secant line, but point slope form. I'm sorry, I apologize. I am very tired. So y minus y1 is equal to m times x minus x1. So what we're going to start out with, the y stays because that's a variable, or a dependent variable, in fact. We know that our y coordinate is 4, and it has a slope of 2, x minus 1, and that's our equation. So next, we want to find an equation of the tangent line at a certain point. I want us to use my favorite definition here. So we're going to find dy dx is equal to the limit as x, or sorry, not x, but h approaches 0 of 2x plus h squared minus 4x plus h plus 3 minus 2x squared plus 4x minus 3, all of that over h. That's a mess, right? Okay. And I think I'm going to move all of this stuff so I can get a bit more space. Undo that, because that kind of killed everything. There we go. Now. Jeez, never had such technical difficulties. So, we're going to start out by expanding everything. So we get 2x squared plus... Ooh, give me one moment. I made a mistake. I want to call this value 3. We are evaluating this at 3. So we want to replace all of our x's with 3's. This is really just a foreshadow of what we're doing in the next video. The derivative as a function. So we actually know what this value at the end is. So I'm going to just insert the value to make it a bit cleaner. So we know that this value at the end is just 4. And hopefully, as long as everything goes right over here, we'll get a 4 to cancel it. So we get 18 plus 6h plus h squared, and actually make that 12h. Twice the product, and then times that by 2. Minus 12h, or sorry, 12 minus 4h plus 3 minus 4. And something's not adding up here. Give me a moment. Okay, I understand what I did wrong. I just misread the problem. This is supposed to be a 9. Alright. So in reality, this is a minus 9. And that means that this is a minus 9 over here. This 18 and this 12, that goes to 6. Plus 3, that's 9. And that 9 is going to cancel off. So, in the end, we're just left with the limit as h approaches 0 of dy dx as x is evaluated at 3 is equal to, factor out an h from everything so it can cancel the denominator, h over h, of 8 plus h squared. Or sorry, plus h. So these are going to cancel, and we'll take the limit as h approaches 0. So we're just left with 8. So then we just have to do y minus 9 is equal to 8 times by x minus 3. And that's our answer. Alright, continuing on. We have now a velocity problem. And this is our second last problem, so I just want to find the average velocity on those intervals. So, if we plug in 2, well, we are going to get 2 minus 12 plus 23. So that's really just going to go to 13. If we plug in 0, we get 23. So, for 0 to 2, our average velocity is going to be 13 minus 23 all over 2. That's going to give us an answer of 10 over 2, or is equal to 5. Okay. So then, what are we going to do about this 2 through 4? Well, once again, we can just plug in some values. Well, we already know the value at 2. The value at 2 is 13. Let's just plug in 4. So 4 squared, that's 16. Half of that's 8. Minus 24 plus 23. And we get 9. Or, sorry, 7. Yeah, 7. There we go. Head math works. So then what we're going to do is we're going to take 7 minus the 13 of before all over 2 is equal to negative 6 over 2, or negative 3. So these two numbers that are nearby 2 are very different. So let's find the instantaneous velocity. That's a bit more useful than the average. So what we're going to do, we're going to take the derivative. So velocity of t is equal to the limit as as h approaches 0 of s of t plus h, which in this case we're evaluating it at 2, minus s of 2 all over h. Well, s of 2 plus h, well, we are going to get 1/2 2 plus h squared minus 6 times 2 plus h plus 23 minus whatever the value at 2 is, which we already know is 13. Alright. As long as everything goes right, this should all cancel. So we're going to expand this out. So we are going to get, let's see, so that's going to go, that squared is going to go to 4, so we're going to get 2 plus, that's going to be just an h plus 1/2 h squared minus 6, or sorry, minus 12, 12h minus 12 minus 6h, and let's see, plus 23 minus, so let's just say plus 13 or plus 10. Alright, so this 12 and this 2, that becomes a negative 10, so that's going to cancel that 10. And all of this is over h. All we have is h's left. So we're going to cancel this h. We're going to cancel that h, leaving a 1. We're going to cancel this h, leaving a 1/2 h. And we're going to cancel this h, leaving a negative 6. Well, this is really just going to 1 minus 6 plus 1/2 h. This is really, and we want to take the limit as h approaches 0, is going to be equal to negative 5, as this is going to go to 0. And that is just negative 5. This last task is kind of easy, so I'm glad. I'm very tired. Alright, so we're going to start out. This graph here is a line, and it looks to have a slope of 2. So we can just graph that. And this is a graph of position versus time. So if you were to actually find the slope, this is just velocity. So let's find a graph of velocity of the spider. So v of t, and versus t, we want this to go 1, 2, 3, 4, 5, 6, 7. All right. So from 1 to 2, it has a positive velocity of 2. From 1 to 2, it also has a positive velocity of 2. From 2 to 3, it actually has a velocity of 0, so we're going to drop it down to 0, and that lasts until 4. Alright. Then at 4 to 5, it actually has a negative velocity of negative 1. Then from 5 to 6, it has a positive velocity of 1. Alright. And that positive velocity of 1 looks to continue on. Well, that's all I have for you today. I hope you enjoyed the following video and found this informative. Hope you have a great rest of your day. Bye-bye.